We've got another very special keynote address with Western Digital. And the title of this is Storage for AI Using GPUs. And their collaboration Western Digital has had with NVIDIA. And we're honored to have two fantastic people who will be presenting. Mark Miquelon, who's currently Product Manager, Director of Partner Alliances for Western Digital's platform business. In his role, he seeks out strategic partnerships that provide additional value to customers that are consuming just a bunch of disk and just a bunch of flash and servers developed by Western Digital. Prior experience includes leadership roles in both engineering and product line management at Seagate, Avago, LSI, Vitesse, Symbios Logic, AT&T, and NCR. And Mark resides in Colorado Springs. And we also have back Rob Davis, who's Vice President of Storage Technology at the NVIDIA Networking Platform Group, where he focuses on ways to apply high-speed interface technology to AI storage solutions. And Rob is a technology leader, visionary for more than 35 years in our industry. And I've known Rob for 29 years when the whole intelligent storage initiative started in the mid-1990s. And prior experience, Rob was Vice President, Chief Technology Officer at QLogic, where he spent 15 years, drove development, marketing for their fiber channel, Ethernet, and InfiniBand technology. He, previous to that, was at Anchor, which served as VP of Advanced Development, Director of Technical Marketing, and Director of Engineering. He drove their development and marketing initiatives of fiber channel in those early days and through the 90s. And Rob is an incredible talent for the network segment of our industry. So please welcome Mark and Rob.
All right, thank you. Thanks for coming out. At Western Digital's Platforms Group, we've been involved in bringing to market products that use NVMe over fabrics on Ethernet for over 5 years now. And what I'm going to go through today is one example that we've recently looked at that's focused on AI. And I think a lot of things this week here are focused on AI, and we're one of those. And it will conclude with a demonstration that you can come out to the exhibit floor and see for yourself. So to start with, I wanted to back up a little bit. So if we think back 5 years ago, before GPUs were so prevalent in server applications, this is really the contents of a traditional server. Uh-oh. There we go, thank you. So we had CPU, memory. You might have SSD, you might not, and you might have hard drive, or you might not, or you may have both. Okay, and that was pretty standard. Could be a 2-socket, 4-socket, 1-socket, a lot of different variants of that, but these were the key elements that were inside that server. And what we see now is GPUs primarily are really driving a lot of change. So if you look at these GPU-enabled servers, particularly the ones that are focused on training your model, you still have the CPU and memory, but memory needs are growing, right? So there are cases where people want to add a lot of memory, and CXL has come along to serve that need. The GPUs, you want to get as many of them in there as you can, and you may also have a data processing unit, depending on what data services that you want to run. And so this is really putting pressure on, where do I put the hard drives? Where do I put the SSDs? And so those are more and more being disaggregated, which means we're moving them out of that box. And it makes a lot of sense because from a latency perspective, you want the things that have less latency to be closer to the CPU. So that's going to be your DRAM, your memory, and maybe your GPU itself. Things that have more latency, like an SSD, or a lot of latency, like a hard drive, can more afford to be disaggregated. And so that's exactly what we're seeing happen in the industry. Some factors here to consider, okay? On the left, I'm showing cost. Now, these may be variable depending on if you're buying capital and putting it in your own data center, or you're leasing access to machines in somebody else's data center. But if you're in the latter, you're definitely going to have subscription and usage fees, right? So every hour that you're running on the GPU is going to cost you a certain amount. Data transfer is also expensive. So you have a big data set. You want to bring that into the data center so that you can do your training on it. There's time, and there's in a lot of cases, money directly paid out to handle that. And then the operational costs, just every day you're going to be running. How much time do you spend on that model? Even if you have your own data center, these things will be capital that you might want to allocate to a given project, right? So it's still a cost. It's whether it's just immediately out of pocket or not. On the performance side, there's considerations as well. So latency, and we've talked about the latency of getting to storage. What I'm going to show you today is actually a way to really reduce that and keep the highest performance that your SSDs can provide to the GPUs, even if you take on a little bit extra latency of moving them out of that chassis. There are computational limits. So power is a big one, right? There's a lot of liquid cooling today. These big GPU servers are definitely consuming a lot of power. And at some point, that could become a limit of what you can actually do. And then resource contention. So if you think of your training data set and the size of it, it may fit nicely inside a single server or it may not. And this is where disaggregated storage can really bring an advantage. We can make it very easy for you to share that data set across any number of GPUs. One key element of this is some technology that NVIDIA has brought to the market called GPU direct storage. And so when you look at a typical I/O, a command would come out to the SSDs. If it's a read, the SSDs are going to put that request, they're going to put that data into memory. And that path goes through the CPU. And then when the GPU wants that data, they would have to go back through the CPU to get it and pull it local. It turns out that this can be a major performance limitation depending on how many other things that CPU is doing and how much data is actually going through there. So when you see the red path here that goes through the CPU, what GPU Direct actually accomplishes is it gives you a path from the SSDs directly to the GPU without going in and out of the CPU's local memory. So it looks a little bit more like the right-hand side, but I've added another change. So those SSDs now are what we call disaggregated. So we've taken those SSDs, and for reasons I'll explain in a minute, we've moved them outside the server. Okay? You notice that we show a lot bigger number of SSDs, so I spoke about the size of your data set could be a big factor in why you want to do this. Once you disaggregate, once you pull the SSDs outside the server, you can put as many chassis full of SSDs as you need onto a single Ethernet fabric and bring them into this GPU Direct model. GPU Direct Storage is designed and architected to use either model. So your SSDs can be local, or using NVMe over Fabric standard, they can be disaggregated and come through this RNIC. And what we are demonstrating shows that you do all that, and there's literally no loss in performance. You get the same great performance as if the SSDs were local, but you get some benefit of having them disaggregated. So we're going to take a little bit closer look at what this actually looks like. So this is the local case, right? So if I look at, in this case, a 2-socket server, the architecture of it, we have just 8 SSDs. The number could be more. I mean, there's servers with up to 24 SSDs for sure, so you could support a bigger data set that I'm showing. But it's pretty straightforward. Okay, you have your GPUs hanging off the PCI bus, you have your SSDs hanging off the PCI bus, and if you think back to the picture I showed before, with GPU Direct Storage, we're just moving data directly through that path. We're not too worried about which CPU it's going through. We've done this analysis, and I'm going to show you the exact GPUs we've used here in a little bit, but in general, the GPUs can consume more data than a single SSD can provide, and we've kind of found the sweet spot with the H100s to be 12 to 16. Okay? And so when I talk about scale and I talk about reasons for having your SSDs be outside the server, you're going to want at least 12 SSDs to be talking to any specific GPU if you want to maximize that performance and get the most out of your investment. It's hard to build a box with 24 or even more SSD slots, right? And so these new GPU servers are really focused on how do I optimize the GPU part, and they should be. And so this really becomes a limitation if you don't do the disaggregation. So in this picture, the light gray box indicates that we've pulled those SSDs out. We do have to add another NIC. So this would be an Ethernet NIC capable of doing NVMe over fabric. But once you do that, I show the same 8 SSDs just to keep the picture simple, but this could be any number, right? Our chassis has 24 SSDs in it. There's some out there that have more, but you can have 10 chassis hooked up to a single GPU farm using Ethernet and Ethernet switching. So some of the benefits is, if we think about 24 SSDs, you're going to remove at least 500 watts and probably closer to 1,000 watts out of your server. So your cooling just became a lot easier. Let's talk about sharing. So if I wanted to share this data set across, say, 10, 20, 30 GPU servers, it's going to be very difficult to do that if my SSDs are inside one of those servers. I could replicate it, right? I could put 24 SSDs in all the servers, but that's pretty expensive. I could run some shared file system. That shared file system, though, is going to greatly hamper your performance. Okay, so if you're going to use GPU Direct and all the performance that it offers, you don't want that to get in the way either. So disaggregating them and letting those SSDs just reside on a fabric, you assign a namespace to a given GPU and let it go. Let it run that data set. Okay, this is one of our examples. So this is actually out on the floor. You can come see it in our booth. We're showing our brand product is OpenFlex Data 24. The 24 is the number of SSDs in the box. So I'm giving you 24 SSDs. We're showing a dozen Ethernet connections to a switch, and that switch is connected to a single GPU server. In that server, we put 2 of the NVIDIA H100s, and we're running a really cool benchmark. We're actually modeling a tornado. So if you come to our booth, you can see this tornado happening. It was a huge data set. I'll give you some specifics of that in a minute. But the key takeaway here is we were able to map 12 SSDs to each H100, and that is the point where the H100 became the bottleneck. So bottlenecks aren't good, but what's good in this case is that you're paying a lot of money for that GPU. You're paying a lot of money for those H100s. It might have taken you a lot of time to get them, right? There's a wait list to get these things. So once you get it, once you have it installed, you want that thing working and crunching your data set all day long, right? 24/7. And we were able to demonstrate that 12 of our SSDs in this architecture can do that. This is an alternate approach. So we're also partnered with another company, Ingrasys. They have a 24 drive system as well. The bridging to Ethernet is done a little bit differently in this case, but the result is very much the same. In this case, we're looking at a slightly lower performing but more affordable GPU, the A100. We put 4 of them in the box. We get very similar results. So these 24 SSDs are able to keep 4 A100s completely saturated, completely busy doing their training on this data set. And with that, I'm going to call Rob Davis to come out and talk through a few of his slides.
Thanks.
Yeah.
I am, first of all, going to thank WDC for inviting me to join their keynote. We're excited to be partnering with them on this technology. And I thought I would start out by letting you see what one of these eBOFs looks like. So here's a picture of it. I'm not going to carry one out. They're kind of heavy. But think of it like a JBOF or a storage system with dual controllers. So there's 2 blades. Each blade, everything in this box is hot swappable. So there's 2 switch blades that plug into the SSDs through the WDC interposer that's inside, and I'll show you the insides in a minute. And the front side is 6. Each blade has 6 200 gig ports, and those are connected by 50 gig Ethernet through an Ethernet switch inside to the interposers. And the interposers are dual ports, so each blade is connected to 24 50 gig ports. There's 24 SSDs, and those SSDs can be any capacity. So if you look at 32 terabyte SSDs, you get 770 terabytes in that box. They can run any protocol the interposer can do. The WDC interposer does NVMe over fabrics with RDMA or with IP. And the performance is really a function of the interposer performance plus whatever the SSD performance is, plus 600 nanoseconds, which is the switching latency of the Spectrum 2, NVIDIA Spectrum 2 switch ASIC that's inside this box. This switch ASIC can actually handle 32 200 gig Ethernet ports, so there's no congestion issues as long as the data paths aren't crossing. One other thing is this is a switch, a regular Ethernet switch. So you can connect other nodes to the front, and they can communicate back and forth just through the front ports. There isn't anything special about this. It's just a standard Ethernet switch. So let's look at it a little bit more. So flipping around the module and looking at the back, there's hot pluggable drive carriers. There's two components in the carriers. One is the interposer, and it doesn't look like the labeling for the interposer made it through the transition. And the other is, of course, the SSD, and they can take any SSD. There's a PCI, it's just a PCI interface, an NVMe PCI interface. And then those, of course, plug into the back. On the bottom there, you can see with the lid off of the switch module, hardly anything in there. There's a switch ASIC and a small processor that has the NOS, the network operating system, on it. There's no data paths through any processors. This is just an Ethernet switch. So they're just straight through from that interposer to the user, as Mark talked about earlier. So where are some areas that we at NVIDIA are exploring to potentially use this exciting new technology? If we look at a data center, typical rack in a data center, you've got obviously lots of servers, GPU servers in our case, and typically, at least in our case, we have some storage also in that rack, some close storage to augment the local storage in those SSD servers. That then connects to a leaf switch. All that connects to a leaf switch, which connects to a spine switch, which connects to a core switch. All those core switches connect through the data center network, and then it repeats, to whatever size that data center is. What we're going to look at, of course, is the storage nodes and the leaf switch, which basically is what you have with an eBOF. Now you might say, how can an eBOF replace that? Because it only had 6 ports out the front. But the truth is that that is a 2 generations, almost 3 generations old Ethernet switch chip. It could actually support 32 200 gig ports, but the latest switch we have, Spectrum 4, can support 256 200 gig ports. So there's plenty of switch ports to handle an entire rack. And you might then say, well, it's just a couple $1,000s difference for the switch and a couple of storage, and you're going to still have to buy a couple of storage servers, and you're still going to have to pay for all those SSDs. And that part's true, but that few $1,000 savings plus the power, plus the cooling, plus the rack space, that gets multiplied by a lot, by every rack in that data center. So this is one area that's very interesting to us because, of course, that multiplies all those cost savings. The other area, and Mark already went through what GPU direct storage is. So the next generation, well, I don't know if it's the next generation, but what we're looking at for potential improvements to our storage stack for GPUs, GPU direct storage is part of CUDA. So it's part of our storage stack that comes with any of the applications that are running on our GPUs through CUDA framework. The new thing we're looking at is called GPU-initiated storage. And what's new here is we're completely eliminating the host CPU from the GPU server data path for moving the storage local as well as remote storage. So GDS actually works with local drives as well. The only difference is instead of using RDMA for remote DMA, it's using DMA for just local DMA. But in this case, again, this new technology called GPU initiated storage, which, by the way, there's a talk on tomorrow at 8 o'clock in the networking storage track, I think it's called. If you want more just on that subject, the architect for it is actually potentially here in the audience, but he will be giving a talk. Anyway, with GPU initiated storage, now you've got a GPU that's running the control path. So it amplifies by literally 2 orders of magnitude the number of requests that can come out of that to those controllers. So as Mark was saying, you can overflow the number of SSDs that are in the GPU server because there's not a lot of space, because there's a lot of GPUs in there. But if you go remotely, you're able to get around that problem by all the things that Mark talked about from the perspective of GPU direct storage. Well, when you go to the GPU initiated storage, that problem is 2 orders of magnitude worse, like tens of thousands of requests coming instead of thousands. And so the eBOF, we think, is very interesting from that perspective. Secondly, because of GPU-initiated storage, we're now able to add SSDs to the memory tier for GPUs. It used to be when we had to go, even for local storage, through the local CPU, there was just too much latency to add GPUs to that tier. But now, and you'll hear more about this tomorrow if you come to that talk, but now we're able to add those local SSDs and remote SSDs to that tiered storage. And what that means, again, back to the problem, we can't fit enough GPUs in that GPU server, is that we'll need to use remote storage. And what's really cool about eBOFs are you can connect them up remotely, and you can add many more drives to get many more IOPS. And if you run out of even one eBOF, you can just keep adding eBOFs as long as you have network bandwidth. And as you saw on the last slide, we're also adding 800 gigabits. So none of these are committed projects. We're exploring it. We're working with partners like WDC on these projects as we explore their capabilities. But we find this technology to be very exciting. And now I think Mark's going to show you the demo.
Thank you, Rob. Yeah, so this is just a snapshot of what we're showing out on the floor, and I'll try to explain it. So there was a bunch of data collected around a huge tornado. I think it was in Oklahoma, and it was a number of years ago. 250 billion grid points, and each grid point collected things like temperature and humidity and barometric pressure and things like that. So multiple data pieces for each grid point are available, and this is available through NVIDIA. It's an example that they've put out there, and we just picked it up and we ran it for this. And so what you see in the green are the results that we get using those H100s, using our disaggregated storage. We're seeing the model absorb and process 90 gigabytes per second of data. Okay, pretty incredible. That results, so the result of this particular exercise is a visual model of the tornado, and you see the picture of it here. If you come to our booth, you'll see it actually moving, right? The tornado is forming and moving and tearing up stuff as it goes. But we can present that at 13 frames a second, and this is real time, right? This is being processed on a couple of H100s real time. And that equates to almost 6 terabytes of data every minute, right? 5.9 terabytes every 65 seconds. Then we can go and we can flip the GPU direct off, right? And we can make the same model process data through the CPU. Okay, and the visual that you see is quite substantially different. So we drop down to 4 frames a second, which doesn't sound like a lot, but when you watch it, it's actually kind of painful after you've watched the good one. And we're only getting 15 gigabytes per second of data through the model. So if you think about how much did you pay for your H100 and all the compute infrastructure to get it running, which would you rather have, right? I think you would definitely argue that GPU Direct is a huge value that you get for your GPU farm, should you enable it. So come by our booth. When you go on the show floor, take a hard right, and we're just a couple of booths down, and we'll show it to you live. Okay, so just the takeaways that you can take out of here. Disaggregated storage is good for your GPU farm. It's very fast. It helps you with scalability, right? If you have this tornado data, you could be running it on a bunch of different models at the same time off of one set of SSDs. So that makes it very scalable, and it's interoperable. We've done everything around this using PCI, NVMe, NVMe over Fabric, and all the Ethernet standards. So it works with a broad range of equipment and connectivity. Thank you. Thanks.
Thank you very much, gentlemen.